Zaplo se to?
No, něco to dělá, no. Jo.
Lebo on zvykne, ako keď sa s ním hýbe, tak zvykne sa trošku spanikáriť. Je to ono?
Jo, je to dobře.
Dobré.
It's a club because the first one is Bartek, I think so. But I
have it for you. Yeah.
just put it
Already one?
here.
There's a second one.
Okay, and how do I make it off?
Oh, you want to hand out?
Okay.
Yes, because I will
Just moderate.
just say
Okay,
a few
okay,
words
just
and
take
then,
this one.
And then
Okay.
I can give
I can put it to
No
my-
problem.
Just for questions. So you can
Yeah, it's already.
And to make it off, just or do not make
I will control it from my console.
szumu.
Czemu?
No to mogę teraz zacząć, to wiesz. Możesz połowę, jak reszta przyjdzie.
Nie, to tam możesz zacząć.
No wiesz, no że spło, nie? Tak naprawdę.
Mhm. No to zaczynaj, bo już patrzę na ciebie. Zaczynaj, bo już patrzę na ciebie. I będą włazić przez 5 minut jeszcze.
Ladies and gentlemen, good afternoon. I would like to welcome you to this session named High Quality Multimedia Applications. My name is Bartłomiej Dzikowski. I am from Poznań Supercomputing and Networking Center from Poznań, Poland. The scope of this session covers aspect of designing, popularizing and securing the high-resolution video and voice-based multimedia solutions. There are three presentations during this session. The first one will be about research on stereoscopic 4K multimedia streaming technologies by Maciej Głowiak from PSNC. The second one will cover aspects of multi-channel streaming for medical and multimedia industry applications by Sven Ubik from CESNET. And the last one will be done by Groove Andersing about VoIP anomaly detection engine. Before we start this session, I would like to remind you about the opening reception tonight. The bus will departure at 7:15 by the Fountain, and we'll have different stops also on the way back. So let's start. I would like to invite Maciej Głowiak from PSNC, from Network Department, to tell us about the research on stereoscopic 4K multimedia streaming technologies for future internet.
Good afternoon. My name is Maciej Głowiak, as Bartek told you. I'm from Poznań Supercomputing and Networking Center. Probably some of you were present on our demonstration half hour ago. So you had a chance to see the 4K 3D. I would like to tell you something more about our research, focusing on stereoscopic 4K multimedia streaming as well as technologies for future internet. First of all, I will introduce the project. Future Internet Engineering is a Polish project. We are doing our software in this project. Then I will tell you something about 4K and 3D technology and why it's a challenge. And then about our research regarding software, hardware, and live streaming. Future Internet Engineering Project, it is called in Polish Inżynieria Internetu Przyszłości, is focusing on network transmission techniques, new network architectures, streaming, new appliances, new applications for internet, for future internet. Our work is mostly related to streaming technologies, but of course there are several activities for future internet, like content area network and streaming, circuit switching. The project is 3 years long. It's about 10 million euro of budget, 19 teams from 9 institutions in Poland. It's coordinated by Professor Burakowski from Warsaw. And PSNC, Poznań Supercomputing and Networking Center, takes part in most of activities. What is 4K? You probably know it already. It's of course the resolution, so resolution higher than HD. It's about 8-9 megapixels, so 4,000 pixels in one line. There are several standards. One is DCI, another is Quad HD, which is 4 times high definition. But it's not only the resolution, it's also the technology for the technology serving such resolution. As you can see on the TV set, 4K monitor, you can see the comparison of existing most common resolution. The red one is SD, standard definition, which is PAL or HD is yellow or green. So you can see that 21 standard definition is in one 4K image. As stereoscopy is being more popular, there are different techniques of watching 3D image. We are using passive polarization here in the demonstration, but there are some others. 4K resolution is 8 to 9 megapixels, so single frame in true color, 8-bit per channel takes 26 megabytes. That's a single frame, so we need 24 or 25 even frames for 1 second. So it gives us a stream about 5-6 gigabits per second, just for a single 4K stream. For 3D, you need double those values. So for 1 hour of 4K content in not the best quality, but uncompressed, it's more than 2 terabytes. For 3D is 4 terabytes, so you can imagine the storage or network. So we use compression in JPEG 2000, which is which is standard for digital cinema. The stream is limited to 250 megabits per second for one stream. For 2 streams is 500 megabits, so you need 1 gig link. For uncompressed, those values are of course higher, and for stereoscopy, you can need for 4K uncompressed stereoscopic image, you need twice 10 gig link or 40 gig link. So it's quite much. Why we are doing 4K and what are problems related to such technology? There are very few solutions for recording, so I mean cameras for processing and visualization of 4K 3D. There is no 4K 3D projector we can buy, so we integrated 2 projectors, but I will tell you about this on next slide. Most of devices are prototypes, so they are not working together. They are not always working together, let's say. There are different interfaces between them, so we need converters. We need additional software or hardware that is not existing. For software, there is limited availability of 4K 3D streaming solutions and players, so we need to create something by our own. And of course, there is but there is very limited access to 4K 3D content, so we need to record it also by ourselves. What are research areas we can define? First is integration of this prototype devices. Another thing is network streaming. We are a network institution, so we would like to stream the video, the high-quality 4K video across the network. So we need software or hardware to do so. There is no software, no hardware for doing it. So our research is software decompression, for example, JPEG format. You definitely know. And there is also better and newer codec, JPEG 2000, which is not the same as JPEG, but it's quite demanding. So we need hardware cards for it. And we are working also on some new architecture for streaming in the future internet. I will tell you about this a bit later. So for hardware integration, as there is no 4K 3D projector, single projector, we integrated two projectors with passive polarization technology, specialized rig for them. You can see it on the screen or behind you. As there is no streaming solution for 4K 3D, we developed a JPEG solution, which is software running on JSON PC. You can see it also behind you in the demo part. And there is JPEG 2000 solution, which uses Intopix Pristine 4 accelerator. For recording, we have different cameras. You can see them in our booth here. We have 4K camera with live module, which is still prototype, but we are working on it. We have Sony cameras for 3D recording. So our goal for network streaming is to develop 4K 3D streaming client-server application. So it means we need software for inexpensive solution. So the software we can run on JSON PC, use it as open source or provide it as open source, use JPEG software decompression, and it's of course cheap because you need just a PC. There is also a professional solution, JPEG 2000 using Intopix device, but it's quite expensive. Single JPEG 2000 accelerator or decoder is about 25,000 euros. So you need two of them, so it's 500. Okay, something more about our application. It's a streaming server and client. Client is integrated, of course, with the player. And we have control application, just a GUI for controlling the streaming. We have several streaming options. I told you about it before. We tested also different codecs like DXT, which is GPU accelerated, but we chose JPEG because for a software solution, because it was more convenient for us just to convert and to use it. We would like to use also 4K live and maybe in the future 4K 3D live with ATAPI frame grabber, which is a live module for Red One interface. Something more about our streaming server. Now we use RTP protocol, so it's UDP transmission, and two video channels, 250 megabits each, but of course we can use more bandwidth with more powerful PC. So now we are using 250. For future internet engineering project, we will use circuit switching network, which is reliable. We can have multiple channels with different parameters, different compression rate in high definition or in 4K. Streaming of different intra-frame video codecs the server is modular, so we can we can choose if we use circuit switching or RTP. The JPEG library we use is libturbo.jpg, and our software is basing on it. It's written in C++ and uses DirectX 9. Now it's using DirectX 10, I believe. So the decoding is done in real time, 24 frames per each eye, so it's about 48 up to 50 4K frames in full resolution. So this stream is about 600 megabits per second. We can increase it up to 1 gig with 70 to 90 compression ratio of JPEG. We are using two ATI cards for displaying 4K. So image for left eye is displayed with one card, and for another eye is for another card. Application is multi-threaded, so you can see the progression of using multiple threads, using just single threads and running the library in single threads. Single thread, we had only 10 frames per second, but using 7 threads is about 50. So that is what we needed. Our PC is quite powerful machine, but nothing so special. It's not server solution, it's just a workstation. That's our server application. Sorry, our client application. So you can see we can have pre-encoded storage of JPEG files, or we can stream it over the network. Then there are several threads decoding JPEG and displaying it using two FireGL ATI cards. For professional, let's say, for professional solution, we use JPEG 2000 provided by Intopix. It's FPGA card, so programmable logic based on Virtex 5 for encoding and decoding JPEG 2000. It's RTP streaming, DCI compliant, which means it can be used in digital cinema. So that's the integrated solution. For 3D, we need two cards with synchronization done in firmware. So we cooperate with Pristine 4 supplier, the Intopix company. They are doing synchronization between those cards in their firmware, and we will do synchronization of sending two RTP streams over the network. They are providing SDK, so we can use it for our own application for testing, quality of experience evaluation, or use it in circuit switching network for future internet. That's the typical use of the Intopix solution. So there can be storage of pre-encoded files, JPEG 2000, sent to decoder, or live transmission. Circuit switching network is, as I said before, is implemented in future internet engineering. Streaming server is modular, so now we are using RTP, but we can use different network techniques such as circuit switching. It will be reliable and it will guarantee stable network parameters. Okay, our next activity regarding 4K and 4K 3D is Red One. It's live streaming for Red One camera. Red One camera is 4K camera without 4K live output. So it stores its 4K movie on hard drives or on compact flash cards, and it has only 720p, so the lower HD resolution. And we would like to steal the stream, the data stream, and to decode it using PC. You can see our engineer working on his office. So we need real-time 4K from Red One. We developed our own board for such task. We transfer data from Red One camera to PC using high-speed interface, but in the future we would like to test also Ethernet connection. Then we use Red Rocket card for decoding and debayerization. And having uncompressed video, we have several options of streaming or using it. We can just show it displayed on screen, on 4K screen, such as projector. But we can also stream it using Intopix or different solution. There are some details of the board. So it's our own development. It's on 4-layer printed circuit board using Spartan 3, which is less powerful than Virtex, but it's enough for such solution. So the data stream is about 22 megabytes per second. We use Red Rocket for decoding, so it's the card, the accelerator provided by Red company. We use high-speed USB 2.0 for PC connection, which is now it occurred. It's bottleneck of this solution, so we think about switching it to Ethernet. The prototype is available in our booth here on TNC, so we can demonstrate it to you if you want. The demonstration we had before this session was streaming from Poznań to Prague. You can see it on a map. It's about 900 kilometers, stream up to 1 gigabit per second, streaming pre-encoded JPEG files, and for visualization we use two Sony projectors. That's our lab in PSNC. I think we don't have time for describing it, but it's also available in our booth, so we can share information about this. That's about the demo here. Tomorrow we have different demonstration, 4K live rendering, and on Wednesday there will be also 4K streaming. Thank you.
Thank you very much for this presentation. Are there any questions regarding this presentation?
Yes?
Hello, my name is Massimo Malabotta. I come from Trieste in Italy. We are a national network, so I'm interested in multimedia applications because they are using much bandwidth and they have to have a low latency. And so my question is, have you tried the live streaming of live camera, and how much latency does have that system?
We haven't tried Red One live streaming because it's still a prototype, so it's not working in production. We tested uncompressed HD. It's about, so single HD stream is about 1.5 gigabit per second. Well, maybe one gig. So it's also quite much for testing. If you have two streams, it's of course twice 1 gig. We would like to test Red One when we have it. I mean, when we have the module for live streaming.
Okay, thank you.
Thanks, nice presentation. The Red One is obviously a professional quality video camera. So one of the questions to me as you move to dual stream for 3D is reference images. How are you thinking about the statistics in not only the frame grabbing, but in the network transport and the frame synchronization across the two cameras or the display when you're projecting it, and then how you're actually keeping track of, for example, jitter and the loss of a frame and what happens from the user's perspective, or how you're actually keeping track of the frames if one of them happens to be dropped? Are you keeping those statistics? Do you have references which you can use?
Yeah. Now we are not keeping such statistics. It's the application is prototype still, so our colleagues, in fact, finished it or finished this stage for this demonstration. So we didn't have time for network testing and measurement still. But of course, we'll be doing such statistics, and we would like to use different network techniques like circuit switching, for example. So of course, the measurement is a very important part of this application for us. Okay, thank you.
Thank you very much for this presentation. Our second presentation, multi-channel streaming for medical and multimedia industry application, will be done by Fenelvik from CESNET, from Research and Development Department. Please.
Sorry, I have the microphone.
Good afternoon. My name is Sven Ubik. I am from CESNET, and I'm sorry. Okay. I would like to present you a summary of our work on what I call multi-channel streaming for medical and multimedia industry applications. Let me shortly introduce CESNET. It's a national research and educational network in Czech Republic, founded in 1996, and it currently operates a hybrid 10 gigabit network based on DVDM trunks. That is, we support both packet switch traffic and circuits switched end-to-end communication. The network is connected to European GIANT network, as well as to the international GLIF network for high bandwidth applications. And we work on a number of national and European research projects. The motivation for the work I am presenting now is that in some scientific and industrial applications, people already use ultra high definition video streams, and those people are often distributed in different areas. And if we can share this ultra high definition video content between different areas with sufficiently low latency, then we can enable real-time collaboration of these distributed teams. Or we can provide new modes of remote education. And there was also our internal motivation that we could leverage our experience in development of FPGA-supported network traffic and processing. So we decided to develop technology with the following basic properties. We wanted to transfer at least 4K content uncompressed for ultimate quality over the network, and the device should be scalable to higher resolution. This should be done with low latency for interactive work, and it should work across regular internet infrastructure, which includes routers and switches, that is not just over dark fiber. And it should be lightweight and easy to deploy. We have developed a device that we call a modular video transfer platform. It's modular in sense of firmware modules that are used for data processing. We use HDSDI interface for video input and output, as it is now a standard type of interface in professional video equipment. Its bitrate is 1.5 gigabit per second, and there is a newer version called 3G, which has a double bitrate of 3 gigabit per second. The device has 8 HDSDI inputs, 8 HDSDI outputs, and a 10 gigabit Ethernet interface. And its primary properties are that it transfers all video content uncompressed. Therefore, the latency of processing on both the sender and receiver together is less than 1 millisecond. The transmission is always full duplex in both directions, and it supports single or dual HDSDI configurations. And it can also transfer embedded audio. The hardware structure is shown on this picture. It consists of 3 main parts: the HDSDI input-output board that processes signals from video interfaces, the FPGA board, which can do more advanced processing, and a transceiver board which carries an optical transceiver for a 10 gigabit Ethernet interface. The main task of the device is to transfer 8 HDSDI channels full duplex over the network. That is 8 channels in one direction and in the other direction. And you can combine these channels for various modes. In one mode, you can transfer one 4K RGB stream, which requires 8 channels. In another mode, you can transfer 2 4K streams with 4:2 color subsampling in each direction. You can combine them in 3D 4K. Or you can transfer 4 2K RGB streams, or even 8 2K or HD streams in each direction. Each stream may have different format, that is different resolution, frame rate, color depth. The device automatically recognizes the format of each channel and can transfer it transparently. And the last option is to combine individual 2K or HD channels into 3D streams. A few other interesting features of this technology are that each HDSDI channel can operate in 2 modes. In full frame mode, we transfer all HDSDI content, that is video, embedded audio, embedded data, synchronization signals, everything. In this mode, it takes about 1.5 gig per second to transfer one channel, and therefore we can transfer up to 6 such channels over 10 gigabit Ethernet. In order to transfer up to 8 channels, which are required for some video modes like 4K RGB or 4K 3D, each input can be switched into other mode, which is a visible frame only mode, when we transfer only video, while the rest of the HDSDI framing is discarded. You can turn, for example, 2 inputs into full frame mode and the rest of the inputs in visible frame mode. In this way, you can transfer 3D 4K with embedded audio in 2 first channels. Another interesting feature is that on the receiver side, the HDSDI outputs to the projector are all synchronized. They are bit synchronized, and the device does not need any external clock source for this function. It can adapt its rendering rate to the incoming data rate using tunable oscillators. We aim at 2 target application areas. The first one are low latency 4K transmissions for real-time remote post-production of multimedia content, or for streaming from events to remote auditoriums. And the other application area are stereoscopic or multi-view transmissions, which can be used, for instance, for e-learning in medicine or other fields, or for remote collaboration in on scientific models, like using the cave environment. The first demonstration of our technology happened in Cinegrade 2009 workshop, where we transferred 4K uncompressed content over 10,000 kilometers from Barandos film studios in Prague to the venue in San Diego. The content was in Prague, while the director of photography was present in San Diego. And he used a parallel video conference to send instructions back to Prague what should be done with the content. The bit rate was approximately 5 gigabit per second. And in the venue, the situation looked like on this picture. The largest screen was the 4K content streamed from Prague. In the lower left corner, you can see director of photography, played by Lauren Hare, who used the video conference on the right-hand side. And he set instructions like, make this part of the picture to be more bluish. And the operator in Prague did this change, and the content was streamed over 10,000 kilometers uncompressed to the venue. Next year in Cinegrade 2010, we did a similar demonstration where we showed how this technology can be used for remote 3D post-production. In this case, it was for 2K resolution. We did not manage the 4K projection in the venue, so we actually used 1/4 of the transmission capacity. But again, the person at the conference venue was able to instruct the person at the data source to do 3D manipulations of the picture, which were streamed over 10,000 kilometers to the conference venue. And this picture shows how it looked like. We actually used 2 receiver boxes in the venue because there were 2 projectors which were physically separated. One was downstairs in the auditorium and one was upstairs in the control room. And we used optical splitter to connect these 2 receiving boxes to the same signal. And you can use the same thing, that is optical splitter or optical multicast, to distribute content to multiple destinations. Another application area where we use our technology is in transmission of robotic surgeries. Robotic surgeries are laparoscopic operations where the surgeon uses 3D vision and an electronic console to manipulate his operating instruments. The advantage is that they generally enable minimally invasive operations with less bleeding, lower stress for the patient, and less fatigue for the surgeon. And a side effect of using 3D vision from the operating robot for the surgeon is that we can use this signal and transfer it remotely to a professional audience for e-learning purposes, like for medical faculties and so on. On this slide, you can see some pictures of the Da Vinci surgical system, which is now dominating robotic operations. It's made by Intuitive Surgical Company. It's now deployed in over 800 hospitals around the world. And it's unfortunately rather expensive. So it's also a subject of some controversy whether the cost is worth the effect and so on. We did our first transmission of robotic operation from the hospital in Ústí nad Labem to an international congress in Brno. It was over a relatively short distance, about 300 kilometers. And it happened in real time. That is, there was a patient which was being operated, and doctors at the medical conference could see the operation in real time. Because the networking delay was also small in this case. It was about 2 milliseconds. And if you add 1 millisecond of processing, so the people could see the operations with the delay about 3 milliseconds. These are some pictures from the audience. They have had also available a parallel video conference, which the doctors could use to ask a question the surgeon, and he answered in real time. Then we did this transmission of 3D HD signal from the surgical robot, again from the hospital in Ústí nad Labem, and this time it was to the Keck Research Institute in Tsukuba in Japan. That is over distance about 17,000 kilometers. These are some pictures from the sending side and from the audience on the receiving side. The networking delay was approximately 150 milliseconds. So the processing delay of about 1 millisecond was negligible at this time. Then we did another demonstration, at this time for a larger audience at the APAN meeting in Hong Kong. This was probably the most complicated network setup which we did for our demo, because we set up a 10 gig path over about 17,000 kilometers. That was from Czech Republic over Netherlight, Starlight in Chicago, Canaria in Canada, Pacific Wave in Seattle, Daejeon in Korea, and finally to the venue in Hong Kong. You will have a chance to see some demos in this conference. They will not be from such long distances as in our previous demos. Tomorrow you can see a demonstration of uncompressed 4K transmission from testnet using our boxes. Again, tomorrow there will be another demonstration in Tycho room, which will be 3D HB robotic surgery from hospital in Ústí nad Labem, and this time it will be recorded. There will not be a live patient. And on Wednesday, you can see using this technology for uncompressed transmission from the cave environment to 3D screen. And this demonstration will be interesting in that it will use software sender and hardware receiver. As for our future roadmap, we plan to add inter-unit synchronization, which will allow us to transfer 8K signals. We plan first small-scale 8K uncompressed demo this year. Then we, of course, plan to continue this technology for practical use in medical e-learning. And it will also be available for other researchers and other users as a pre-production unit later this year, supporting 8 full duplex HDSDI transports and XFP pluggable transceivers to 10 gigabit Ethernet. And that's it. Thank you for your attention.
Thank you very much for this presentation. Are there any questions?
Yeah, just a question to your medical transfer. I mean, is it really realistic to have medical operation in real time transferred via a multi-purpose, multiplex packet switch network? I mean, would you like to be dependent on that?
The last part of the question was if we want...
Would you like to be... I mean, if somebody is doing an operation with you, would you like to depend from a video transfer on a multiplexed general purpose network? Just this is just a question. How I mean, I see very good results from a transfer, but I just think about how to apply such thing in medical environments.
You mean the privacy issue?
Yeah.
Of course, the patient has to, in advance, sign that the data from the operation can be used for scientific purposes, and we usually use dedicated end-to-end circuits for a particular venue.
Are there any other questions?
I would like to ask if you are going to use 3G SDI interface as well as dual link, because now it's dual link, right?
Yes.
And are you going to use 3G SDI?
We have some plans about 3G, but there was not so far any pressure from applications. So when it comes, then it should not be difficult because the hardware itself supports 3G. I mean, the chips which are on the board, that's already designed for 3 gigabits per second. It's FPGA also supports that. So it's just a matter of firmware.
It could be useful, especially for 8K. Then you don't need 4 boxes, just 2, right?
Yes, it would also require larger FPGAs with a larger
exactly.
number of fast channels.
Okay, thank you.
One let's say, business question. When you developed the boxes to do the streaming, you did it on your own, or you managed to get the collaboration from the industry or other stuff like that, from the outside world?
We did the development was done on our own in CESNET. Of course, we collaborate with external companies on demonstrations, which help us to get very useful feedback. And we now have a project to turn this prototype into a product, and this project is in collaboration with 2 companies.
Thank you.
Thank you. Just one quick question. Could you give us more comment about how the doctors reacted to the demonstration you made in terms of usage case for the health usage? My question being that they used to do that with traditional VC, then we enhanced this to HD, then you made a demonstration with 2K. Now you have in roadmap 8K. When is the resolution enough from a doctor perspective? Is the 8K will enable more than 3D image? Could you comment about that?
These are 2 different application areas. For medical purposes, I think HD is sufficient, and also the robot provides HD resolution. We can't get high resolution from this device. So 4K and 8K, that's for another application area, like for collaboration in post-production, in multimedia industry. So these are 2 different application areas.
So today, are you saying doctors are okay with HD, or they are asking you for going to 8Ks?
They generally say that it's a very good picture, and that they even if a doctor who operates with the Da Vinci system sees the 3D picture transmitted, then he says that it looks more detailed than what he can see on the console of the actual robot.
Thank you. Thank you.
Thank you very much for this interesting presentation. Our last presentation for this session will be with animal detection engine, and this presentation will be done by Mr. Gurvinder Singh from Uninet. His responsibilities includes security aspects of SIP-based communications. Please, welcome.
Thank you. Hi. I'm Gurvinder Singh from Uninet. Mic check. Today I'm going to talk about a little bit in brief about the Uninet SIP project infrastructure, and later in detail about the security aspect of it, which we built to detect the anomaly attacks. Because in the SIP, you can have a kind of really high cost calls in international or to some service numbers which will charge a lot of money. So we really need kind of security mechanism there. So Uninet actually started to learn about the SIP protocol in general about around 2005 or 6, and then we just started closely following its improvements, and then from this year 2011 we actually implemented and deployed a SIP infrastructure for all the higher education sector in Norway. And this infrastructure, we have centralized session mode controllers which are having a highly redundant trunks to PSTN providers, and also it has a really high capacity. So we have tested actually on our system like 10,000 simultaneous calls, and these calls are only to the PSTN world. This call doesn't include the SIP to SIP traffic. So you can have further maybe more than 10,000 calls between the SIP to SIP clients. And we are continuously monitoring the capacity of this trunks. And if we see that it raises more than 80%, and then we can actually have an alarm, and then we can quite fastly we can actually add another systems if we need it. And this year we plan to migrate at least 10 universities from ISDN or legacy PBX to SIP world. And we already, until in this first half of the year, we have 7 universities already signed up for this, and the work is going on in progress. And by next year, we will be migrating 20 more universities, which will be roughly around 80% of the higher education sector of Norway, which will be migrated from SIP from ISDN world to the SIP world. And we live usually in a kind of heterogeneous world. So in the PBX side, there is no surprise. So we have like media gateway from Nortel, from Ericsson, and Alcatel. So we need to provide all this connectivity from this legacy PBX to SIP world. So for that, we provide media gateways to all these systems. And for each university, when they migrated from ISDN world to the SIP world, we populate their numbers into the enum golden tree. So in this, enum is a kind of a service actually which allows for a caller to make a call in the SIP using the SIP protocol, and this call doesn't cost anything. So it doesn't matter actually wherever you are in the world. If you make a SIP call, it will be free. So using the enum gold tree, it's helpful for the researchers to connect with them without costing much money to the institution. So this is the infrastructure which we have. So on the down left hand side, we have this 3 legacy PBX from Nortel, Alcatel, and to connect them to the Uninet SIP network, we have media gateways provided in front. So for example, if some institution has already migrated to SIP or completely, then we just have their SIP PBX which directly connect to our SIP infrastructure. And there is another quite common now and getting popular system is from Microsoft. It's called Link, which does have a kind of some basic support for SIP protocol, but it's not really kind of open SIP. They have their customized SIP, so we need to provide a media gateway to work with the completely standard up SIP Connect to make it a SIP Connect compatible. So we provide a media gateway for that. And after when the call is made from the institution, it comes to our SIP network, and then it goes to the Uninet session mode controllers. And through there, actually, this call enters into the PSTN world. And we have then redundant networks here and links to the PSTN world. And all the calls which are then made through the session mode controllers are logged into the call detailed record database there. And the security engine which we have built is actually learning the call behavior of the institution from these CDR records. And then if it detects anomaly, then it raises an alert. So in this project, our main focus has been actually to the open standards. So as mentioned that it's an heterogeneous world, so we really need open standards to have an interoperability between the systems. So and later is the focus is on providing the video integration and messaging integration also with the voice. And and the world is getting smaller and smaller, and people just like to traveling, and mobility is one of the basic requirements these days. So through the SIP, actually, we can use it quite easily, because then we can have soft phones, so people can have access to their office phones directly on their laptop, so they don't need to have a fixed office space, so they can move around. And humans are particularly, in general, easy with the name. So with the SIP, we can have actually a kind of single contact point. Your email address just becomes your phone number. So just write down just SIP : and your email address, and it will dial to your office phone directly. And the system itself is quite scalable, so that's why we made it open to all students also. So students at least can make a call on the SIP world. To the PSTN world, the students will not be able to make a call to the PSTN because it charges money. But if any institution would like to do that in any university, so it can be possible also. So this was a little bit in brief about the current unit SIP project and this update. So now we will talk about the security aspects, which are the engine which we have built upon this. YPD's anomaly detection engine is based on the behavioral learning algorithm. So this learns the call pattern behavior of each institutions, and then keep monitoring its call pattern. If it detects any anomaly in the pattern, then it raises an alert. So under the hood, it uses the machine learning, which was around for quite a while, but people have this kind of a mind setup that doesn't work actually outside the lab environment, in the production environment. But in this specific case, it works because people tend to don't deviate from their call pattern. So the people who usually make a lot of calls, they make a lot of calls actually every day, and the people who don't, they don't. So in overall institution's call pattern behavior actually doesn't have much randomness in it. There is only randomness comes when either in act of emergency, or if there is any festival coming, or is people having a lot of vacation gone, so there was no calls, and once they came back, so there is just a sudden spike when they come back. So these changes can be actually configured in the engine so that it doesn't raise the false alerts. The engine itself is quite modular and customized. It can be customized according to your needs, and you can actually make it how much sensitive to the changes. So it can be really lenient on the changes in the network, or it can be really aggressive and raises the alerts. So these are the different modules in the system. It's the CDR module is actually the module which connect to the database and fetches all the call related records for this specific institutions for which this engine is running, and then this all fetch record will be sent to the detection module, where it runs the detection algorithm and see if there has been any anomaly in that fetch records or not. If there is an anomaly, then it raises an alert. So the alert is then later on sent to the specific institution by the method which has been configured. And in the configuration, then you can specify some configuration details, which I will describe in the later on. And in the logging, it just logs any errors in the systems, or any based on your logging level, it can be information or error or debug information. So in the configuration module, the engine uses a libyML library to load these parameters, and it provides quite a high configurability, and there are few of them which have been listed here. So, for example, when you want to start a training, so you have, for example, data from February, call detail records, and you want to run the engine for whole February month. So you can actually specify the start date, 1st of February, and duration for whole month. And then you know that there has been attack, so you don't want to learn that behavior. So you can just, the engine will just stop until for how long duration you have mentioned, and then it start the detection. For example, if there hasn't been any attack in the month of March and April, so you can say that rather than going through that logs, which are pretty much same, you don't really need anything interesting there. So you can actually say that you can just start detection from the current date or specific date from which you want to start it. And you can specify what's your office hours. So it can be lenient on the spikes during that office hours. So for example, if you have an office hour from 8 to 4, then during this time, if there will be sudden spikes due to some office meetings or some specific agenda came up, then it won't raise the false positives during that time. And then these are the sensitivity and adaptability. These are the main parameters actually, how it adapts and adapts to the changes in the pattern behavior. So these value actually has to be really tuned to a specific institution traffic pattern. And another is the run mode. So if you, for example, you have an call data records from last year and you know there was an attack, but it's really hard to find out which number was causing the alert, causing the attack, or which was launching the attack. So you can actually run the engine, and this will actually identify quite easily, and it will tell you that this was the number. So you can run it in the offline mode rather than the online mode. And another last parameter is actually the minimum number of calls or duration. For example, in your institution, you have high call traffic. So you can tell that in specific interval, if you have 1 hour of international calls or 100 mobile calls, that's no problem. That's quite common to your institution. So you can actually tell these minimum numbers, and this will increase the performance, because then the engine will not go through this specific minimum that interval of these calls records, and then save the time performance wise. And the CDR module, which I already mentioned, that it fetches the records which is collected by the session mode controllers, and that records is the information which is required is the call date for when the call was made, who was the caller which made the call, and to whom the call was made, and the duration for that specific call, and the institution code, because this infrastructure is running on a national level, so we need to know actually to which institution this call belongs, so that we can actually charge this, and in case of alert, we can actually alert that specific institution. So we need the institution code also there. And the call type is a type of the call which is made. So either it was an international call, or it was a mobile call, or it was made to a service, or it was to a domestic number. So there are specific, you can actually identify the calls, and then you can run the engine on these specific calls. So you don't want to monitor the domestic calls because they are free. You don't want to monitor the emergency calls. So you can actually specify that you want to monitor only international calls, mobile calls, and the service call. So engine will actually monitor only these specific calls. So the core of the engine is actually this algorithm called Hellinger distance algorithm, which actually learn the call pattern. It uses this mathematical formula. This actually calculates the probability of the previous interval to the current monitored interval. So it actually, the distance value which is calculated for frequency of the calls and duration of the calls. So you can have an attack in which people are calling to specific numbers where, for example, some service number can give you the money to just to call them. So you can have an attacker which is just calling to this number and just hanging up. So the frequency of the call in that case in the attack is really high compared to if you have in the normal traffic. Or you can have some attacker actually who is just calling to international number for 2-3 hours. So then in that case we need the durations. So this actually monitors both things to detect an attack. So this diagram shows actually how the engine works. So in the first part is actually this is a training period. So whole training period is actually divided into delta t times of intervals. So in these, so by interval slices actually it calculates the distance value, and then based on the distance value it uses a statistical gradient algorithm to compute the threshold. And in this calculation of the threshold value, it uses the sensitivity and adaptivity value which we have configured. So based on that, it can be lenient on the spikes and really aggressive on the spikes. So it just it actually then continuously learning also. So for example, in the later on in the next stage, when it's when the learning is over, training is over, then it start to testing period. So in that interval, if it sees that this traffic pattern was legitimate traffic pattern. So then it actually adapts to it and then change its threshold value based on the traffic which it has observed in that interval. But if this traffic was really high or it wasn't a legitimate, then it will not learn that behavior. So it's hard for an attacker to trick it to raise its threshold value so that it can make more calls. So what happens if it has detected the attack already? So it then sends out an alerts based on the method which you have configured in the configuration module. So it can actually send an alert to the syslog, or it can send to a Simon or a big brother, which can later out send an email or SMS to the responsible administrator or specific person of that institution. So what's in the alert message? Alert message contains the timestamp when the attack was happened and the status message, that is an what kind of a higher security attack or critical or fatal based on that, and institution name to which the attack belongs, and the alert ID. Alert ID is a ID of the call records on which the attack has been detected. So all the call records in which the attack has been detected, these are logged into a database which can be retrieved later on. So we have a web service actually where the administrator later on can log on and see if there has been an attack, and then put that alert ID to browse on the call detail records. So in that, there are specified the call types. So there was an international calls which caused a detection alert, or there was an mobile calls, or who was the caller, to which destination call was made, and the duration. And so based on the call types, attacker can actually block the specific call types from that specific institution for the time up to he want, so that actually it can minimize the cost. So if there is a international calls which was made by the attacker, so the institution can then specifically block the international calls. So it don't need to turn its institution phone infrastructure down, so so that the user will not be having the downtime. So user can continue making the mobile calls or domestic calls. They don't need to be having the denial of the service in that sense. So this is actually kind of a graph which shows how the algorithm actually learns the behavior. So the starting point is actually when it has just finishes the training period. So it's just like a kind of how when we start to learn when we just start to do something new. So we have to keep practicing it, and with the time we get better and better. So it's similar in this algorithm. So with time it adapts, it learns the traffic pattern more and more accurately, and then get in the end you will see that it's actually getting quite really good in getting the threshold and distance value. And I have data from an old attack which happened at our institution in last year, early January 2010. So during the first, in the first part, in the 0 to 2000 time, actually you can see there is quite a lot of spikes together. So this is the time actually when the attack has been happened. So the engine was able to detect this attack in the first two intervals when the attack has happened. So, but this was an old detailed records on which we run the engine. That time this engine wasn't in production, but right now it's in the production, and it's running on and monitoring all the calls which had been made in our SIP infrastructure. So this is another graph which shows actually how the algorithm actually adapts to the traffic changes. So there are some spikes on which there is no change in the distance value or in the threshold value, but the spikes which are lower than the threshold value, so it actually based on that value it actually goes a little bit up or a little bit higher. So the amount how much it goes up and down, it depends on the adaptability value which you have been specified and configured. And the future work we have at the moment is just monitor on the call detail records which have been made. So we have planning to actually monitor the registration behavior also, because sometimes we see now that the attacker is actually just trying to register itself with the fake username. So the frequency of that registration is much higher compared to the normal legitimate registration behavior of an institution. So this algorithm can, based on that, can also raise an alert. And also now, as this system is already in production, so we will be learning and from this experience and further tuning the algorithms or customizing it to perform better. And it would be interesting if some of you have some more ideas specifically for this to get the feedback, so we can actually improve that in that sense. And that's it. Thanks for your time. And this software is available, it's an open source, it's available at this given URL.
Thank you very much for this interesting presentation. Are there any questions?
Thank you again for your presentation, really interesting. If I correctly understand, you do not drop any calls, you simply monitor all the traffic. So the question is, how fast are you able to react when an attack is enacted? So how fast are you able to stop or to manage that?
Yeah, I think I have to go to those, just those. Yeah. So this is actually, it depends actually how fast you can detect the attack is depend on the delta T value. So if, for example, because it actually waits for the next intervals. For example, if you have a delta T for 5 minutes, so it will not run the algorithms until the 5 minutes is over. So it will monitor all the call detail records in last 5 minutes which it has received and then run the algorithm. So if you want to have really high response time, so you can actually reduce this delta T to 1 minute or maybe less than that if you would like. So it's all depend on that configuration.
So, but the system is able to detect this attack and stop the attacker.
The thing is, like, this is a detection engine, not a prevention engine. So it will raise an alert and it will send out the alert to the person and then he will actually block the call.
So my question is this, and when the person receives the alarm, in how many time is able to react to the attack? So,
so the thing is, like, because we didn't actually make it a prevention at the moment, because it might then end up in giving a denial of service. So we really, at the moment, we don't want to have a prevention. We just want to have a detection. And as I mentioned, that we will be learning with the time how it should be deployed in a most ideal state. So maybe if we see that there is a need to make it a prevention, then we can actually make it happen to make it a prevention then.
Okay, thank you.
You're welcome.
Hello.
Hi.
This is interesting, okay, the prevention to monitor. Can this be applied to other services? I'm thinking of web sites, webmail, video conferencing, other stuff. Can this be applied to that?
This whole depends on actually how much randomness in your system, your services is. Because as I mentioned that in this system, the randomness is not so much in the call pattern behavior. So, in this algorithm which we're using, it actually, this might not be able to cope up with so much randomness. But we have another project which will be looking on statistical algorithms for anomaly detection in normal network. So from that project, I'm hoping that it will be more suitable algorithms will be popping up actually, which will be more general to some general services.
Okay. Yeah. And the other question is, if an attacker starts attacking very gently, it will be learned on your curve, right?
Yeah, but then we are talking about an intelligent attacker, which knows the internal of the system which you are already running. So that's always kind of an really hard to detect that specific attacker. Yeah.
Thank you very much for this interesting speech.
Yeah.
Thank you very much for attending this session. I think it was quite interesting. I would like to remind you once more about the bus. The departure is 7:15 from the bus place near the fountain. Thank you once more and see you soon.